Okay, I'll be right back with it. So I want to make sure I can clear my nose just in a brief second. So let's see here. All right, and we're back. So for this one, number 13, it's asking us to calculate pH of 0.20 moles of solution of NH4Br 5 degrees Celsius. So for this question here, we have to really understand what exactly is going through like the equation. Like what do we end up with? So NH4Br, realistically speaking, will dissociate into, so kind of go like this. It takes two steps. NH4Br, then typically likes to just dissociate completely. NH4 plus Br minus. So with that being said, we now can just focus on this NH4 plus part, because we last checked in the acid sheet, HBr, hydrobromic acid, is a strong acid, so it's not going to want to form again. You won't see hydrogens in there. Try to make it into hydrogen or hydrobromic acid. Okay. So let's just go on to solve that. We have, let's see here, NH4 plus water, H2O, is going to turn into NH4 plus, cannot forget the plus, NH3. So now it was deprotonated, it lost a proton, plus H3O plus, which was protonated. Okay, so now we have that formula. We need to know exactly what the pK value, the K value of ammonia, ammonium, NH4. So NH4 is all the way down here. Ammonium ions, 5.6 times 10 to the negative 10. So Ka for ammonium is 5.6 times 10 to the negative 10. And now we're ready to make our ice table, as they say. Okay, so our ice table, because water, as you can see, should not be counted towards the ice table because it is a liquid. We're only going to have, okay, for the ice, NH4 plus, okay, and we're going to now have NH3, and we're going to have H3O plus. Now for ice table, we have the interstitial change equilibrium. And now let's see what happens here. So our initial for this is, as I said, 0.20 moles. So as you can see here, 0.20 moles, which translate over here, which translate over 0.20 moles. Okay, so that's what we start with. The rest start with nothing, okay, because nothing has been made yet. So now we want to see what changes. It's going to be minus x plus, whoops, that should be zeros, not x's. And now it's going to be plus x plus x. So now we have two x's here to symbolize how much H3O and NH3 was made, and this would be 0.20 moles minus x. Now for this, as I noticed, the concentration is so much more stronger than the Ka value. So what actually happens here is that because it's much greater than 1,000 times of the Ka, it's like 0.2 divided by 5.6 to the negative 10. So 5.6 to the power of negative 10. It is over 357 million times stronger. So pretty much what's going to happen here is that our NH4 is not going to lose anything really. It's still going to round up to 0.20 moles. So in reality, our our Ka equation, where it's Ka is equal to products over reactants, which is NH3 H3O plus over reactants NH4 plus, okay, when we actually now start plugging in numbers, you're going to see that the Ka, which was 5.6 times 10 to the negative 10, is equal to now x squared, because that's the two x's of the products, divided by NH4, just 0.20 moles. So what we have to do here is that it's going to be 0.20 moles times 5.6 times 10 to the negative 10. Okay, then we have the x squared still. So now the square root of all that would give us the x, which accounts for the amount of ammonia produced and the amount of H3O as well. So we have 5.6 times 10 to the negative 10 times the 0.2. Okay, and then the square root of it. We get x is equal to 1.0, whoops, let's make sure, 1, 2, 3, 4, 5, 1.058, that's a good number. Oh, there's only 2 then, 1.1 it seems, because the significant digits, as from what I can tell, is 0.20, which is only 2 sig digs, so it's going to be 1.1 times 10 to a negative 1, 2, 3, 4, 5. That tells you now in this solution we produced that amount of ammonia and not hydroxide, hydronium. Alright, so now to find out how much, and that is in pH, we need to use this formula. pH is equal to negative log of H3O. So now that we have that equation, we're now going to figure out what it is. So we're going to plug in that value of x, so negative log of that answer. Our pH for this solution is sitting at 4.97. So in regards to the pH of a solution of NH4Br at 25 degrees Celsius, that 25 degrees Celsius wasn't really necessary. It just kind of makes you reaffirm that, okay, we're dealing with standard temperature and pressure, just so that way you can continue on with solving it how you would. So they said, which is what we did here, they want you to create an ice table. We do not need the water side, hence why they have it dashed out. Then we know they found the literature value, which is 5.56. We use 5.6 times 10 to the negative 10. So it's going to be x, and 20 minus x. And then what happened here was that they just simplified it to where they probably just did what I did, made it just equal 0.2 instead of doing a whole quadratic equation. Actually, they did do a quadratic equation. Nonetheless, though, as you can actually see, that our numbers that we got are literally almost exactly the same, even though I used the shorthand, because that's how much concentration we had relative to the Ka value. So now with that being said, though, the pH of that, when you convert it all, they get 4.98. only reason why I get 4.97, well actually it is 4.98 because it's 4.975. So that's where I just didn't round correctly. Numbers did vary slightly, so that may have played in, but at the end of the day I should have rounded correctly there. But luckily we were able to get that answer. So this will be the steps you take in order to find the pH. You make sure you have this correct formula, you draw an ice table out, you fill in the values, and then you plug it in to your pH. That's how you do it. So question number 14. So this is correct. All right. So we have 14